Okay, I'm going to wait just a couple of minutes or a couple of seconds here for people to drop in. All right, let's get this started. Welcome, tech art enthusiasts. Welcome to another episode of Tech Art Talk Live. My name is Chris, and I will be your host for today's session. Now, last week, we gave a quick introduction to ray tracing. Now, we just gave some of the basic insights of what ray tracing is. Today, we are going to continue the conversation on expressing okay, what is ray tracing exactly good for, and how can it be implemented and combined into our everyday workflows and our processes? So without further ado, I've got a lot of slides here today, and if you have any questions, feel free to drop in when I'm lecturing. Go ahead and drop in, give me a contact, and then let's get this show on the road. We've got a lot of slides to show. Okay. All right. There we go. Okay, very good. All right, let's go. All right, now just to rehash a little bit from where we were last week, I got to give all thanks to Eric Haynes and the folks at NVIDIA for coming up with a lot of the content for this. Now, mind you, I studied ray tracing a lot when I was a undergraduate and as a grad student, but in between the times of that, I kind of let it sit still. So the folks over at NVIDIA did a great job of kind of like bringing up a refresher course up there. And here is the link to all things wonderful ray tracing. And I would highly encourage anyone interested in the subject to explore these links. All right, now last week we said, okay, ray tracing is good, but it's very expensive and has high overhead, but therefore rasterization of what we're typically used to is also good, and it can get things done in real time. So what the best idea is to create a hybrid example of where you got some parts that are rasterized and some parts that are ray traced. Okay, so let's talk about this compromise, this hybrid combination. Okay, they're going to be used together to exploit each other's strengths. They're going to maintain real time. You're going to use rasterization to get an initial view of the scene, and then you're going to use ray tracing to get the glossy lighting effects that make it look so awesome. But why bother with all this? What is ray tracing actually good for? Okay, why is it so much better than rasterization? Well, we have to go and then realize that what we're dealing with is we are dealing now with go back to the rendering equation. We're trying to render something that is photoreal or as close to photoreal as possible. And that all heralds back to the early days of CGI back in Cornell, where they created the Cornell box, where the professor created two scenes, one as a model and one as a CGI render, and he asked the students, which one is real? Is the one on the left real or is one on the right real? Good question. But let's look over to see what ray tracing is actually good for. Okay, ray tracing is really, really good for creating hard shadows. Look at these shadows on the surface here. We got the shadow beneath the globe here, the shadow against the cube. It's really, really good for creating nice hard shadows. It's also really good for creating nice soft shadows, where multiple rays can be cast from the light source through the object, and then those values can be averaged in order to create a nice soft shadow. So ray tracing, great for shadows, hard shadow, soft shadow, you name it, ray tracing is great for it. Okay, ray tracing is also really, really awesome for doing interreflections, which means is that you notice that the side of the cube has a kind of a red hue against it, and this one has a kind of a green hue against it. That's because the photons bouncing off of the walls are projecting light onto the surface, and it's picking up an actual green surface. So therefore, it's really good for indirect lighting, color bleeding, and overall global illumination. Similarly, ray tracing is also really, really great for glossy reflections and refractions. Now remember last week, whenever we cast a ray into the old scene, that immediately a reflection ray was cast and a refraction ray was cast. So that just goes to say that ray tracing is great for reflections and great for refractions. But here are some things that you may not have known about ray tracing. Ray tracing is also really, really great for generating ambient occlusions. Now, ambient occlusions, in case you don't know, are the nooks and the crannies and the deep recesses inside of the scene that light has a really, really hard time getting to. And when you combine the ambient occlusion in order to make your scene just a little bit darker, it adds a little bit of extra life and a little bit of extra vitality into your scene. Now, how does ray tracing actually help with this? Well, if you notice here that if you cast a ray onto the surface and then bounce it around, then you can immediately see what parts of the object the rays are hitting. Now, if you move that back, then you realize, okay, then this object or this point here isn't really contributing to the overall global illumination of the object, and you can see it just very few points of it actually reach the actual destination surface. Okay. Ray tracing is also really good for, whoops, I'm going backwards. Okay, let's go forward here. Ray tracing is also really, really good for creating depth of field. Now, depth of field when you're rasterizing is a very expensive process. But depth of field is the camera effect of where you have objects that are inside of the field of view of your camera lens, and all objects either outside or closer than that field of view are going to get blurred. And so here's a situation of where the objects in the forefront are in the field of view, but all objects behind them are in the background, so they're going to get blurred out. Now, it can also be returned just the same. The object in the background is now within the field of view, and the objects in the front are then blurred out. So depth of field, very, very good, very, very easy for creating when you're ray tracing. Likewise, motion blur is really, really good. Now, motion blur is tough because when you're rasterizing it, then you got to render a whole bunch of frames and then blend them together. Now, with motion blur, you can render certain objects and just render parts of the scene over and over again until you get those multiple views, which then can be rendered and composited black on top of each other. Ray tracing is really good for creating atmospheric. Look, we've got some fog, we've got some atmosphere, we've got some God rays, all very, very, very good using ray tracing. Caustics are also really, really awesome for that because the caustics are hard to simulate, and it's just a process, and therefore all of it, you'll notice that it looks like this person created, it looks like a Voronoi breakdown of the overall surface. Well, I'm not going to tell anybody that we've got a Voronoi surface here, but anyway, the Voronoi and the rest of the caustics are empowered through ray tracing and make it very, very useful. Okay, what else is it good for? Okay, faster light baking. All right, if you go ahead and use ray tracing to bake all your lights, suddenly a real complex scene, for example, from 14 minutes can get down to about 16 seconds using ray trace baking. Ground truth. Now, what is ground truth? Ground truth is the exact visual target you're trying to strive for that you really want to try to get, and producing a ray traced ground truth is going to be really good for creating that correct solution for comparison. Now, this is really good for developers when they're really developing new and improved rendering concepts. And I've seen other people go ahead and just abuse it, where they use ray tracing for collision detection and volume rendering and other such craziness. Okay, now the rasterization pipeline deals with 7 primary stages. Now, I don't think we've gone through and actually created a lesson about this, but this is something that I fundamentally teach within my shader writing course, and it's very, very important. But there are 7 stages of the rendering pipeline, and they go according to this. You've got the input assembly, and then that goes to the vertex shader, then that goes to the tessellation, then it goes to the geometry shader, then it finally gets rasterized, and once it's been rasterized, then it goes through the pixel or the fragment shader, and then all of the rendered layers are then blended together. Okay, it kind of looks like this. You've got a draw call, which is one single material or one single texture instance. And then it goes into the scheduling of where it then goes ahead and enters into the vertex shader. Then it gets rasterized. Then it goes through the pixel shader, and then all of the layers get blended together into a final rendered output. Now, the ray tracing pipeline turns all this on the head. It changes everything. Everything's going to change. There are now 3 primary stages instead of 7. And they are the ray generation, the ray traversal and intersection, and then the ray shading portion. Okay, 3 stages. Now, there's going to be a lot of organization. Why? Is because there's a lot of scheduling and there's a lot of rays bouncing around, and all the rays can be recursive. So that means one ray could spawn multiple rays, and those rays spawn other rays, and so this turns into a logistical nightmare. So a lot of overhead that needs to be kept track of. Okay, how does this look? You've got the ray generation generating the initial pixels, or generating the initial rays. Then this goes through all the scheduling. And then it goes through the traversal and the intersection stage. And then once it's gone through that, it goes through more scheduling because, when it intersects objects and traverses objects, more rays are being created. And then it finally goes through the shading stage. And then once through the shading stage, then it might get returned right back to the scheduling and then start rendering some more rays. So what this means is that there are going to be 5 new types of shaders. Now, inside of the ray generation stage, you've got one shader that is called the ray generation shader, which kind of like is your initial shader. And most of the time, I think this is going to be basically by default, but we'll have to wait and see. It defines on how to start tracing the rays. Now, during the intersection stage, then you have the intersection shader that defines what the ray is doing when it intersects an object. It could bounce, it could get absorbed. Who knows? It depends on the material, right? Okay, now we have to deal with the then we have to deal with the actual shaders, where it goes through the shading stage. And there are 3 different types of shaders. And the first of these is the mist shaders. Now, when a ray doesn't hit any object, we have to tell the ray tracer what to do and how to handle it, and that's handled with a mist shader. When a ray actually hits an object, then we have to actually go through the actual rendering process, and that's primarily done in the closest hit shader. Now, when you hit an object, sometimes that object might be transparent or semi-transparent, and that means that it's not only got to spawn new rays, but it's got to keep that ray continuously going. And when it goes continuously into a transparent object, that's when the any hit shader comes in. Now, the any hit shader is kind of like the redhead stepchild in this overall diagram, and I think you'll see why in just a little bit, because it is run once per hit, and then every time it hits an object and goes into transparency, it gets created again. So from an eye chart version, this is what the 3 stages look like. You've got your ray trace call in the far left stage, and then it goes into the traversal loop. And there are a whole bunch of stuff going on here, and there you can see that it checks to see if it is intersecting objects, and then depending on that object, it asks is it opaque or not, and then if it is transparent, then it goes through any hit shader, and then when it just gets moving along, and then finally it says, do I have an actual hit? And either it's yes or no. And if it's yes, then it goes through the closest hit shader, and that's going to be about what the regular fragment or your pixel shader does today. And then you have your mist shader, which is what to do when the ray actually misses any objects and just goes flipping off into oblivion. Okay, all that gets calculated and then it gets returned back to the ray tracer. All right, from a logistical version, it's a little bit more simplistic. Once again, the ray generation stage kicks off rays. It goes through something called the acceleration traversal. We talked a little bit about that last week, and then it kind of like checks along with the traversal. It checks for intersections. When it does find intersections, it checks if they're transparent or not, and then it finally comes through and it says, okay, am I done with the traversal? And it says yes. Then it goes either into the closest hit shader or it goes into the miss shader. Okay, so this any hit shader is, like I said, a little bit of an anomaly because as we saw in beforehand, it's actually not part of the ray shading or the actual shading portion stage of the ray tracer. It's actually in the traversal loop. And so that's why it's a little bit of a redhead stepchild. And it is an optional stage and is used primarily for transparency. And it kind of kicks off here and then it goes through the intersection stage, and then when it does hit an intersection stage, it immediately goes into an any hit shader, and then it starts testing if this object is transparent or not. And then finally, it just keeps going through that loop over and over and over again until it finally goes through and asks, does it have an actual successful hit? And if it does, then it goes into the closest hit shader. And if it doesn't, then it goes into the miss shader. Okay. Now, ray tracing is also called path tracing, and path tracing is where you spend not just one ray going through every pixel, but you send a whole bunch of rays going through every pixel, and it can be very noisy. Now, if you look at the image on the far left, you can see that this is the kind of noise you get when you only have 5 samples per pixel. The one next to it is 50 rays samples per pixel, then 500, and then 5,000. Now notice that it takes going up all the way to about 5,000 rays per pixel in order to get rid of this noise. And regretfully, the amount of sample or the sample rays per pixel has diminishing returns. If you notice here that this crown, which is a very intricate model, it has 5,000 samples per pixel, and it's very tight. But when there's 1 sample per pixel, and then 4 sample per pixels, all the way up to 16, and then up to 50, you'll see that it's got a huge big jump in quality just going from 1 to 50, and even 1 to 16 is actually pretty darn good. But you have to ask yourself, do you really want to spend 5,000 samples per pixel? Okay, if we're going to do that, sending 5,000 samples per pixel, how are we going to keep it real time? This is crazy. This is like one of the reasons why ray tracing takes so slow. Well, you start with a noisy image at a low sample count, and then you reconstruct it using various denoising techniques. We're going to talk about what these denoising techniques are in a little bit, but with one sample, you can generate an image that looks pretty darn good. Now, denoising itself can be very fast, and here you have as a scene that is halfway rendered with 1 sample, and the other half has been denoised. It can actually look pretty good. And here's another image where you've got half of it is been sampled with 1 sample per pixel, and the other has been denoised. Now, this denoising effect could be just simply reserved for various effects types. Now, suppose that you were using the ray tracing just for your shadows, and you're using rasterization. Well, then that could help speed up your process, because then 1 sample can be sent in order to check out and compute all the ray tracing samples and denoise that. But if it's still done for every pass, it can still get very, very expensive. So instead of waiting till all the passes are done through the rasterizer, what you could do is wait until the final pass is done. And then once the final image is all put together, then you can actually go and do the denoising. And now this I wanted to do is introduce some of the denoising, as this is where a human is creating some of the denoising themselves, and this is where a neural network is being used. Yes, a neural network, you heard me, AI, deep learning. This is where the connection between ray tracing and neural networking or deep learning is being used. So deep learning is being used to denoise the overall process. Okay, so if you know anything about neural networks or about AI, well, I guess we'll talk about that too. But really, in a nutshell, it starts with you taking a whole bunch of rendered images that are supposed to look like what the objects are supposed to look like. It goes there and it creates the neural network. And then once the neural network has been successfully trained, then it's plugged back into the ray tracing so that every pixel then is then plugged back into the neural network and then post-processed again in order to get rid of all the noise. This actually works pretty good. It's actually pretty nice. And so the data is used to infer what the image is going to look like. Okay, now I've got a bunch of examples here, and this is not my video. This is a video from NVIDIA, and I wanted to show you what some of these denoising techniques can actually look like. Okay, I'm going to move this up to about 4 minutes. Hopefully you're not hearing the noise from the actual video itself, because I really want to just focus in on the video images themselves. Okay, let's go ahead and play that. I'm going to go ahead and turn that volume. Okay, so you see here we have 1 sample per pixel where you've got ray trace shadows. And then if you use the denoising, the shadows here look pretty darn good. Now, if you compare that to traditional, okay, if you're going to ray trace that, this is going to give you the ground truth. But if you compare that to good old shadow mapping with rasterizing, then you're going to see lots of artifacts, the stuff looks good, and you see Peter panning all over the place. And Peter panning is when the characters are floating above their shadow and the shadow looks disconnected with their overall body. Okay, now the next thing I wanted to show you is right around here. If you take a look at these reflections, you have 1 sample per ray trace reflection, and then you add the denoising, and then here's what the ground truth. So the denoise sample looks very, very similar to the denoise, and they look pretty darn good. Now the ground truth is when the full 5,000 samples per pixel have been allowed to go, and you can see that they're very, very clear. And so if you were to combine this with the stochastic screen space reflections and the reflection captures, you get stuff that looks pretty good. Some of the reflections look a little bit sketchy, but otherwise things are looking pretty sharp. Okay, now the other part that I wanted to show you is over here at global illumination. Here we go. Now the global illumination, here is a studio scene that's been rendered with 1 sample per pixel, and here it is, the same scene with global illumination and denoising turned on. It's actually looking pretty good, and here's the ground truth. So it's not real far. The denoise thing is not real far away from the ground truth. They're very, very similar and good looking for each other. Now here's an animation that's showing what this is actually could look like. Now here's an animation with, I believe, of what the ground truth could actually look like. As you can see, it's very smooth. There's good motion blur, and all the objects in there is looking very natural, and the global illumination is looking fantastic. Now here is where it is denoised. And this is where 1 sample per pixel, and this is a denoise with 4 samples per pixel. It still looks a little bit blurry, but with the movement and so forth, it's still looking pretty good. Okay. Now, once we get through this, then we're going to show what the overall, some of the overall effects actually look like. And you can see it actually looks real good. Now, what this half is on the reference, which is in the full-blown truth, and here it is denoised at 4 samples per pixel. And you'll notice here that the sample per pixel is actually looking pretty good. All right. So denoising is the whole reason why ray tracing has suddenly become real time. And it's the reason why that ray tracing has been making quantum leaps just in the last few years. And this is the reason why we have real time ray tracing. And so in my humble opinion, ray tracing is the reason why you all folks as tech artists need to start learning about machine learning right now. neural networks, I'm doing it myself every day. I do just a little bit every time, and I'm learning piece by piece. And maybe I'll actually give a quick lecture on how, the basics of neural networks in the future. That might be a super topic. Okay, that pretty much covers what I wanted to, at least as far as ray tracing is concerned. And this covers all that I had hoped for to cover, kind of give you an introduction into ray tracing. And I look forward to using it in the new consoles and the new UE5 as soon as it comes forth, because I think it's going to be really, really, really super important. Okay, great. Now, if you liked what you saw today, go ahead and subscribe to my video channel. And if you want to, go ahead and check me out on Facebook and check out Tech Art Talk Live on Facebook, as well as Chris Rhoda on LinkedIn. And you can check both of those out on LinkedIn. And otherwise, thank you very much for joining me. Next week, I think next week will be my last broadcast of the year. And so I'm going to kind of like deviate from the whole rendering situation, and I'm going to just go with and describe one kind of oddball tool that I'm a really, really fancy for, and I really, really love, and it could make any tech artist go from here up to a quantum level by just understanding it. And that simple tool is called regular expressions. And I want to cover just a quick introduction of how to use regular expressions and how they can make a TA look like a superstar. All right. I look forward to seeing you again all next week on Tech Art Talk Live. Until next week, bye.